Fluorine is the heavyweight champion of the chemical elements. Its entire existence is defined by an extreme, unmatched hunger to consume electrons. This vintage periodic table plots out the elements, and if you look specifically at the top right corner, you find the throne of chemical power, right where fluorine sits. But understanding that power leads to a recurring point of confusion. Chemistry uses two completely different metrics to measure an atom's hunger for electrons: electron affinity and electronegativity. This simplified grid shows the pedagogical trap that catches students. As you move from the bottom left to the top right across the table, both of these metrics increase simultaneously. Conflating these two terms obscures a crucial physical distinction. A lone atom floating in the vacuum of space behaves very differently than atoms bound together in complex biological structures like DNA. To map the building blocks of the universe accurately, we have to split our perspective into two distinct contexts: the atom in total isolation and the atom in a relationship. Let's start by creating a total vacuum. We strip away all surrounding atoms and molecules to focus entirely on one single isolated element. In this isolated state, we measure electron affinity. This is an exact reading of how strongly that lonely atom wants to capture a loose extra electron drifting by. When an isolated atom successfully pulls a passing electron into its shell, a mechanical reaction occurs. The atom physically expels energy, measured in kilojoules per mole. The group 7A halogens release the most energy. Grabbing one electron gives them a perfectly stable noble gas shell. Elements located at the bottom left of the periodic table have almost zero desire or capacity to pull a free electron into their orbit. Electron affinity is strictly a measurement of isolated desire. It represents a lone entity's capacity to grab a free floating electron out of the void. Now we abandon the vacuum. We move to a scenario where two atoms are already locked together, mutually sharing electrons in a covalent bond. This is where electronegativity comes in. Once atoms are bonded, electronegativity measures the strength of a specific atom to pull those mutually shared electrons back towards its own nucleus. In 1932, the chemist Linus Pauling created a mathematical scale specifically to assign numerical values to this competitive force, which brings us back to fluorine. On the Pauling scale, fluorine scores a maximum of 4.0, making it the ultimate electron hog within any chemical bond. Think of a covalent bond as a literal tug-of-war. If muscular fluorine bonds with weaker hydrogen, fluorine exerts a dominating pull on the shared electrons. It doesn't snap the rope, it simply hogs the electrons, keeping them far closer to its side. Unlike electron affinity's metric of a single atom capturing a rogue particle, electronegativity is purely a competitive power dynamic over shared resources. Because we have clearly separated the isolated vacuum from the bonded relationship, we can use electronegativity as a predictive cheat code. By subtracting the Pauling scale value of one bonded atom from another to find the difference, chemists can predict exactly how a molecule will behave. If the two atoms have the exact same electronegativity, the subtraction results in a zero. This mathematical tie creates a pure non-polar covalent bond, where the electrons are shared equally. But consider the opposite extreme: fluorine at 4.0 against cesium at 0.7. The mathematical difference is massive, ending the tug-of-war entirely. The stronger atom severs the connection, stealing the electron outright. This violent theft abandons covalent sharing entirely, forging an ionic bond. These invisible mathematical rules dictate the tangible results we see in test tubes and beakers. The numbers on the scale determine the physical materials and reactions we observe in real-world laboratories. Tracking the directional trends of the periodic table provides us with a clear map of atomic power dynamics. Those simple numbers dictate exactly how the entire material world is constructed.